Thank you. Thank you for the introduction, and I want to thank the organizers for having me here. First, can everybody hear me and see my screen?
Yes, we can.
Thank you. So I was asked by the organizers to discuss van der Waals heterostructures of 2D materials, and arguably I'll provide a short survey of some important properties. I want to say at the outset that I'm not going to advance any particular biomedical application, and candidly, I think it's perhaps too early to say with any confidence whether the van der Waals heterostructure will have biomedical applications, largely because the issues of throughput and scalability that were discussed earlier perhaps are even more stringent for van der Waals heterostructures. But this is the type of meeting that effectively helps us inform one another on the various needs of different domains in science and engineering. So hopefully this will be informative for for those of us listening in, and certainly it's been informative for me. This is the one important slide of my talk. I want to acknowledge the students that did the work that I'm going to discuss today, or some of the work that I'm going to discuss today. Some of them are still with me, but most of them have moved on. Collaborators at UT and elsewhere, Arizona, UT Dallas, as well as the collaborators in Japan that supply hexagonal boron nitride. This is the dielectric of choice today for people working in van der Waals heterostructures. This is a brief outline of the talk. I'm going to be discussing high mobility electrons in HBN, hexagonal boron nitride encapsulated heterostructures, with an emphasis on transition metal dichalcogenide, just because this has been a semiconductor that it's been discussed yesterday and today, thanks to the nice introduction by Shintong. Then we'll discuss a couple of properties that are perhaps more exclusive to van der Waals heterostructures of 2D materials. That would be coherent tunneling in double layers, and also I'll touch a bit on moiré patterns that can be implemented in twisted bilayers and multi-layers of 2D materials. So 2D materials, this is a very brief overview. They've been discussed quite extensively already in this conference. We have graphene that consists of carbon atoms in a honeycomb lattice. It's a semi-metal with a relatively high mobility. A peculiar property of graphene is that it has a linear energy momentum dispersion that it's illustrated here. Okay, and it has a Brillouin zone that it's similar to the direct lattice. It has a hexagonal unit cell. The corners of this Brillouin zone are typically referred to as the K points, and that's where the band minima are in graphene. And in proximity of this K points, there is a linear energy momentum dispersion that departs, for instance, from the prototypical quadratic energy momentum dispersion that we would see in a gap semiconductor. Now, a close material that has the similar lattice as graphene is hexagonal boron nitride, with the difference that one atom of carbon is substituted with nitrogen, the other one with boron. A sublattice asymmetry in graphene opens a gap. This is one structural way to introduce a sublattice asymmetry by substituting one site with one atom, boron, the other one with nitrogen. And this turns from a semi-metal into a high gap semiconductor. Has a band gap of 6 electron volts. It can be considered a semiconductor, but for practical purposes, hexagonal boron nitride in van der Waals heterostructure is a supporting actor. It's a dielectric. And occasionally a tunnel barrier. And then this family of semiconductors called transition metal dichalcogenide, they have a chemical formula MX2. M is a transition metal, X is a chalcogen, that would be a group 6 element. The transition metal could be, in this particular case, a group 6, molybdenum and tungsten are the most often used, and they form a semiconductor. And in the monolayer limit, as Shintong very nicely illustrated, it's a direct gap semiconductor with the band extrema again at the K point, the corners of the Brillouin zone, which is also hexagonal in this case. This is, so I should say historically that ever since the graphene was exfoliated down to the monolayer, not long after people managed to exfoliate other materials, transition metal dichalcogenides, they came before the hexagonal boron nitride. And not too long after, people started to wonder, okay, now we've gone down to the monolayer, can we now build structures that combine these materials perhaps in a way that depart from what we would see in natural crystals, and also perhaps with different properties that can be engineered in these types of structures. And the heterostructures that arguably elevated the field in the early 2010 and shortly thereafter is the hexagonal boron nitride graphene heterojunctions, or graphene encapsulated hexagonal boron nitride. And that's because hexagonal boron nitride, just like graphene, is atomically flat. It has a very low concentration of defects, doesn't have charge defects like other dielectrics, for instance, like silicon dioxide. And as such, it provides a very clean neighboring environment for the electrons in graphene. And as a result, electrons in graphene encapsulated in hexagonal boron nitride have a mobility that is high, typically 100,000 centimeters per volt second. It's common at low temperatures, but even higher values have been reported. Another peculiar property of graphene on hexagonal boron nitride is that because these lattices have a similar lattice constant, there's something that forms here that's called a moiré pattern. That's because there is a superlattice that forms in this particular heterojunction, and that's illustrated here. Okay, the wavelength, it's in the order of 10 nanometers. And as a result, it creates replicas in the band structure. So think of it as having a superlattice. The wavelength of the superlattice would effectively create, a different Brillouin zone. And the manifestation of that would be that instead of having a single charge neutrality in that heterostructure, there would be replicas of this. Okay, and you could see here maxima in resistance as a function of a gate bias in this particular data, and that has to do with this restructuring of the energy momentum dispersion. And in magnetic fields, there was a very compelling demonstration of something called Hofstadter butterfly that probes the fractal nature of the energy levels of electrons in a periodic potential combined with a strong magnetic field. A very widely used heterostructure, graphene in hexagonal boron nitride, reveals very high electron mobility, as well as cloning the Dirac point in graphene. Now, for people that are familiar with heterostructures, but perhaps, let's say, covalently bonded materials, when we think of heterostructures, certainly when I think of a heterostructure, I think of bonding the atoms in a vertical direction. That's what provides the functionality of heterostructures. And that's why this is effectively the effect that people that have been working on heterostructures for a number of decades have been harnessing, the concept of band engineering. So really, the functionality of heterostructure derives by coupling atoms in the vertical direction and modulating the band structure. The heterostructure that we saw when we have graphene bounded by hexagonal boron nitride, really the boronite is a passive actor, it's a dielectric. So the question that becomes right away is, can we implement something like this in 2D materials? And if so, how would we probe it? Okay. So I'll illustrate here a phenomenon that probes this and also allows a quantitative understanding of, for instance, coupling of one atom to the next one in the vertical direction. And this phenomenon is called resonant tunneling, and it can be pictorially illustrated in the manner shown here. Let's say that we have 2D materials. Let us assume that they have a quadratic energy momentum dispersion, if we focus at the band minimum. And then if the band structures of the two 2D layers are aligned energetically, we can take an electron from one layer to another through perhaps a tunnel barrier. And in doing so, we conserve both energy and momentum. Tunneling is allowed. But on the other hand, if somehow we mismatch these band structures in energy space, either by applying a bias of some type, a gate bias or an interlayer bias, If we conserve energy, we don't conserve momentum and vice versa. And this is illustrated here. If we were to take one electron from here and moving it to the opposite layer, we may conserve energy, but don't conserve momentum. So as such, if we enforce momentum and energy conservation, we can have either high or low interlayer tunneling, depending on these two conditions. And this can be modeled in a manner shown here. And this is a phenomenon that's been probed in heterostructures of 3,5 compounds, and as I'll discuss also in 2D materials. And there are some advantages of this phenomenon in heterostructures of 2D materials, as I'll illustrate shortly. Now, in order to probe this, let us perhaps get more practical and have a look at how we actually make heterostructures. So I will start with, let's say, some materials that have been already exfoliated and inspected, just like Xintong showed earlier. So this is graphene on silicon dioxide, hexagonal boronite, and a TMD of MOS2. And then we'll use a technique that is typically referred to as a pick and place that allows sort of the assembly of 2D materials in a desired order. And in our lab, and I guess in a number of others, we would use a hemispherical handle that's shown here schematically that's coated with an adhesive polymer. And that allows us to basically pick up different nanomaterials and then also release them on desired targets. This, by the way, this type of technique could actually be adapted to other nanomaterials, not necessarily 2D materials, and that could actually perhaps have some practical applications for biomedicine. The one way to implement this is to use a mask aligner. So the hemispherical handle would be somewhere here, and then the sample with the 2D layers would be here. We load it in the mask aligner, and then we make use of the micro manipulation in the X, Y, and Z direction that the mask aligner allows. But since then, we've also implemented a setup with other types of positioning mechanism. So pictorially, let's say that we have identified the flakes as shown earlier. Let's say we start with hexagonal boron nitride, we land on, we pick it up, and then we go to a different location or maybe a different wafer which has a transition method like alcogenide. We pick that up also, and we can iterate this, and I guess typically we iterate with a number of layers. And then when we're satisfied that we have actually picked up the layers in the desired sequence, we release them by changing the substrate temperature. And then typically electron beam lithography, metal deposition, and sometimes etching is also used to finalize the device. So let's look at the actual device. I'm showing here, I'm going to show the tungsten diselenide encapsulating hexagonal boron nitride. So we'll start with hexagonal boron nitride, which is going to be a substrate, and we're going to pattern the contacts first. So the contacts are going to be patterned first. This is a device design that enables lower contact resistance, particularly for transition metal like alcogenide. So this is the bottom substrate with the contacts, and then we exfoliate tungsten diselenide. We do PL or Raman, just like Xintong described earlier. And then if we're satisfied that the flake has the requisite quality, we pick it up with a top dielectric of hexagonal boron nitride, and then land it onto the bottom contacts shown here. And then we do E-beam lithography to pattern a top gate, that is a metal gate in this case. There are devices where we prefer a graphene gate, depending on the requirement of the device. So this is the one example of a process flow, and this allows the electrons in a transition metal like alcogenide to have a higher mobility. And I'm showing here an example of what's called magnetotransport, measuring the resistance of the electrons. Those will be holes in monolayer or bilayer tungsten diselenide as function of magnetic field. These data shows quantum oscillations as a function of magnetic field and quantum Hall effect, and that has to do with the discretization of the density of states, the emergence of lambda levels in a high magnetic field. And this is generally a fingerprint of high mobility electrons. The typical mobility in these samples will be of a few thousand, let's say maybe 2,000 to 5,000 centimeters per second. So just like with graphene, the electron mobility in TMDs can be improved by encapsulating it in hexagonal boron nitride. One effect that we can also control is rotational alignment. And this is important in a heterostructure because direct alignment of the lattices also translates into a direct alignment of the Brillouin zone. And this is particularly important if we're interested in electrons moving from one layer to another, electron coupling from one layer to another. It's important for them to be at the same location in momentum space. Okay, that would ensure that, for instance, the electron momentum is a good quantum number across the heterostructure. In a, let's say, in a covalently bonded heterostructure, this is generally a given because heterostructure grown by chemical vapor deposition or molecular beam epitaxy, thanks to the chemical bonding, will necessarily be registered from one plane to another. But in 2D materials, that's not necessarily a given, and the way we would address it is using something that the community refers to as tear and stack or cut and stack. And this consists of taking a larger grain of a 2D material and splitting it into one or multiple segments and then picking them up sequentially. And if we do that, we would ensure that all these segments would have aligned lattices at the outset, and we can either keep them aligned or twist them controllably if we desire to do so. So let's examine one such heterostructure that's a bit more complicated than the one we discussed earlier. So this is bilayer graphene with the tunnel barrier here in between. So tungsten diselenide is going to be a supporting actor here. It's not going to be a semiconductor, but simply a tunnel barrier. And one thing I would say is that these two lattices are rotationally aligned, so that ensures that electrons in one layer have the same momentum as the electrons in the other layer when they tunnel. So this is the heterostructure. This is a transmission electron micrograph. This is a sample that we've sacrificed. You see here bilayer graphene, transition metal dichalcogenized. Those are the outlines of the layers. And then we'll pattern contacts to the individual layers using e-beam lithography and metal deposition. And what you see here, when we measure the interlayer tunneling characteristic, you see this very sharp negative differential resistance that stems again from the energy and momentum conservation of one layer, electrons from one layer to another. If the layers were not rotationally aligned, this would not be possible, but rotational alignment enables this resonant tunneling. These type of tunneling characteristics tend to be very robust with temperature. So I'm showing here data from 1.5 Kelvin to 300 Kelvin. And this is something very distinct, for instance, from electrons in 3,5 compounds or silicon, germanium heterostructure, where this the tunneling characteristics seem to be very immune to temperature. And that has to do with basically with the 2D confinement of electrons in graphene. And we can model this quantitatively, and there's good agreement between the experimental data and simulation. One modeling parameter that comes out of this agreement is what's called the hopping energy of one electron going from one layer to another, and this is really measures the, if you want, coupling from one layer to another. In this particular case, it's a relatively small number, 30 microelectron volts, but this is an example that we can have a functional heterostructure in a vertical direction, much like one would do with more conventional semiconductors. And again, the physics of this tunneling can be explained by examining the band alignment of the two layers as a function of gate bias on one hand, top gate bias, bottom gate bias, or interlayer bias. The gates, what they do is that they dope the different layers, and then an interlayer bias, a voltage difference between the top layer and the bottom layer, creates a Fermi level difference between the two layers. And this resonant tunneling, this very high conductance, occurs when the bands are aligned. So what I'm showing here with green and red are the bands of the two layers, and they overlap, but their Fermi level could be different. Okay, so when this condition is realized, that's when tunneling is favored. And then when this condition, we're away from this condition, tunneling is suppressed, hence this gate tunable negative differential resistance. So this is one sort of interesting effect that is somewhat, it's not easy to implement in 3.5 or silicon germanium heterostructures, even more difficult to make it gate tunable. And in 2D semiconductors, thanks to the 2D nature of the confinement, this is easier to implement and also appears to be rather immune to temperature. The same effect could actually be implemented where we have a transition metal dichalcogenide as a semiconductor and hexagonal boronite as a 2D layer, as a tunnel barrier. And in this case, we would have tungsten diselenide, and hexagonal boronite as tunnel barrier. Similar effect, very resonant tunneling with negative differential resistance, very sharp resonances. There's an interesting physical effect that takes place here. Because of the spin-orbit coupling, the electrons would spin up and spin down separate in energy at the K point. And depending on whether we have the two layers rotationally aligned or one misaligned by 180 degree, we can actually align bands with either spins pointing in the same direction or spins pointing in the opposite direction. And depending on this alignment, we can have either very sharp tunneling when we align spin up bands and spin down bands, and shown here. So this would be when the two layers have a zero twist between them. And if we have a 180 degree twist between them, we would suppress that because spin wants to also be conserved during tunneling. So in this particular case, we may align the bands energetically, but the spin points in the opposite direction. So that tends to suppress the tunnel. So let me discuss now this last topic of control moiré patterns in van der Waals heterostructures. So far, we've made an effort to align layers in order to keep the momentum as the same quantum number for different layers in the stack. What we'll do now is we're actually going to introduce a control twist between the layers, and what that does, it introduces a sort of a spatial modulation in the physical landscape of where the electron moves. And that also will translate into a different momentum space restructuring. So the Brillouin zone is going to become much smaller just because we have a longer wavelength here in this heterostructure. How we do this, we would start with two segments. So these two layers, they stem from the same large grain. They've been isolated using, in this case, lithography and etching, but they're rotational, they're aligned. They stem from the same larger grain. So therefore, the crystal axis of these two segments is this R point in the same direction. We'll pick one up, then twist it slightly and land it on top of the other one. So then in this overlap area, there's going to be a twisted graphene system. Then we would add the top gate, metal gate, or graphene gate in this case, and then metal contacts, quite a few processing steps here. So this is the end device. And then what we will see in this type of device is this phenomenon of replicating the neutrality point that I mentioned initially. So if we had a single layer, we would see a charge neutrality point when the sample is undoped, and then the conductance would become high. But then there would be locations here when the resistance goes up very sharply and there is an insulator. And that is the location where we have filled out a Brillouin zone of this moiré pattern. Remember, in real space, we have a large wavelength. Therefore, in momentum space, the Brillouin zone is very small, and therefore we can fill it up electrostatically with electrons. It's very interesting. So what's shown here is the band structure in the momentum space, and these points are the K points of the Brillouin zone of the moiré system, this thing right here. So these will be the Brillouin zone of the starting layers, and there is a Brillouin zone of the moiré system shown right here. And very interesting, there are angles where the electrons in these bands have very interesting properties. They slow down almost to a standstill, and when they do that, other interesting properties emerge, such as superconductivity, ferromagnetism, and also correlated insulator. So this is maybe low temperature physics, and I will not discuss it in this presentation. And also, candidly, as I said, I don't think there's any credible application of these phenomena for biomedicine. But perhaps for the students listening in, it's instructive to have a closer look at how correlation arise in these moiré bands, particularly in flat bands. So as I said, if we take the two layers, we twist them in real space, there's going to be a twist in momentum space, and there's a very small Brillouin zone of the moiré pattern that could actually be filled by electrostatic gating. These are calculations, so the bands can be very flat there. And the way to understand it is, let's say we take two parabolic bands. These would be the twist in momentum space, so this would be the two minima right here. And if they hybridize, this steepness right here disappears, and we end up with a relatively flat band. Let's see what happens when we try to populate flat bands with the gate. So this is a energy momentum dispersion. And then if we were to populate it with electrons, we put 2 electrons per unit cell, I guess 4 electrons, 2 per spin, 2 per valley. And normally we would expect to see a resistance that changes the gate voltage in this manner. At the bottom of the band, it would be large. In the middle of the band would be low. And again, the top of the band would be large again, because we have filled the band. Experimentally, what people see is that there would be insulators that actually emerge in the middle of the band. Why is that happening? So there would be insulators where there would be a large density of states otherwise. And the way we can understand it is we can take this flat band, make 4 copies, 1 for 2 spin and 1 for valley. And then let's pretend that it's basically they're very flat. And then when we have these flat bands, but they're degenerate, something wants to break the degeneracy. And that something is actually electron-electron interaction. And we see this phenomenon in other instances. Whenever we have a degeneracy, any imperfection would actually like to break that degeneracy. In this particular case, electron-electron interaction wants to break that degeneracy. And as a result, these levels actually are split by interaction. And as a result, whenever we try to populate a moiré flat band, correlated insulators would emerge in the middle of the band. In this particular case, a quarter and half filling associated with the lifting of the valley and spin degree of freedom. So this brings me to the end of the talk. I hope I convinced you that van der Waals heterostructure of 2D materials have some interesting properties. Perhaps the most relevant one for application would be high electron mobility, but there are some other interesting properties that may find applications in the future. I think it's too early to say that. And I'll stop here and be happy to take your questions.
Thank you very much. Does anyone would like to ask a question? I don't see any questions. Maybe we can see if people come up with questions in the brainstorming session.
I have one question before we move on. Emanuel, I know you said a lot of this is done at low temperature. Can you elucidate what temperatures are used here?
Actually, a lot of what I showed, it can also be done at room temperature. So for instance, the resonant tunneling that I discussed, that is a room temperature phenomena. It is robust between 1.5 Kelvin and 300 Kelvin. The electron mobility in either graphene or transition metal like chalcogenide is the highest at the lowest temperatures, but advantages can be also seen at room temperature when either TMDs or graphene are encapsulated in hexagonal boron nitride. Certainly moiré physics, it's only a low temperature phenomenon.
Okay, and do you know if I know this is all very emerging stuff, so I think it's nice to have gotten to expose everyone to what people are doing next. But I mean, I guess the most near-term possible applications that may be affecting these biosensors that are being built because they're similar structures in terms of being flat structures that sense things. Do you know if any work is being done in that area yet at all?
So I think there's probably a question. I think Deji would probably be better positioned to answer. I think there's a lot of work in you know, as you may know, in sensor of 2D materials, and you know, a lot has been done there. I think there are many questions, you know, about specificity and other things. So 2D materials, by their very nature, they will form a chem-FET, and certainly I think sensing is an application. I think specificity is probably you know, the most important question to be asking in that regard. But you know, from a standpoint of making a chem-FET out of 2D materials, I think that is readily feasible.
Thank
I
you.
did see another question popped up.
Yes. Sarah, I don't know if I'm mispronouncing your name, so I apologize in advance. Do you have a question?
Yes, thank you, sir, for this workshop, this presentation. And I have some doubt, some basic question related to when, what should be the minimum channel region for calculating the device property?
So I guess in, you know, certainly, you know, micron scale is sufficient to, you know, to see any on all the properties that we discuss here, being either tunneling or field effect in transport. Transistors can be made with channel lengths that can be very small, certainly below 100 nanometers. So there's no, I guess, you know, even probably close to 10 nanometers. So there is no, I don't think that the channel length has to be, I guess, it's something that is a key factor for the properties that we discussed. I think that too large channel lengths, then questions of uniformity of 2D materials, they come into question. Yeah, there may be questions about uniformity, but in this particular case, what I've discussed here, it's not something that depends strongly on the channel.
And sir, sometime when we study about the spin property,
Mm-hmm.
then as I'm working theoretically, so spin should be provided at the edges of the atom, or spin should be provided whole over the atoms. What should be the best criteria to calculating spin property?
So every block state would have a momentum and a spin. And I guess for semiconductors, those block states, they're effectively delocalized. They span the entire crystal.
Entire the crystal. Okay, sir. Sir, recently I published a paper regarding NDR effect in boron nitride nanoribbon field effect transistor. And I think my work is totally matched with your work, but your work is, sir, experimentally. And this is the good for me, as I've learned more from this seminar, this presentation. And sir, what should be the maximum gate voltage we can provide on transistor? It can be 40 volt, 30 volt.
Well, the gate voltage as a number per se is not, you know, that's not the important number. I guess what matters is what is the field across the dielectric. And
okay.
Typically, you know, it's I guess it's of the order of megavolts per centimeter for hexagonal boronite, similar to perhaps you know, silicon dioxide. So the breakdown field of hexagonal boronite, if that's your question, it would be not too different than other dielectrics like silicon dioxide.
Okay, sir. Thank you. Sir, one more question. Sir, when we reporting about the NDR effect, tunneling effect, so is it good to report about the eigenstate or local density of state at the both voltages? There's a peak voltage and current where we observe, and low valley voltage where we observe the minimum current. So what is the role of eigenstate?
So this is a question that I guess probably we can take it to in the breakout session, but in essence, what I guess one would do, you would have the band structures of both layers as a function of gate bias, as well as the interlayer bias. So those would be calculated using an electrostatic model. And then depending on how you couple them, a tunneling current can be computed once you have the band structure and the hopping energy from one layer to another.